Your first milestone for your project is due whenever the homework is due. Is that next Friday? Next Friday. And there's some instructions up on the course website. They're very simple. There's not really many guidelines you have to follow. It's just trying to give you some guidance in terms of what your project topic should be about, and then the format of your proposal. So don't stress out too much about that. You can't really get a bad grade in the proposal unless you don't do it. And it's just a way for you to get feedback. We'll give you some feedback once we have a chance to read them. You'll get assigned a TA mentor. Each TA will be kind of serve as a mentor to some of the projects, and then you'll get some feedback. So remember to work on that, and you have your homework coming up as well. So we have maybe like a third of a lecture on subgradients to do today to finish, and then I'm going to dive into the subgradient method. So last time we talked for a good bit of the lecture about subgradients, which, to remind you, just were kind of a generalization of the notion of a gradient for a convex function, in the sense that they were vectors that gave us this property at a particular point x, holding for all other points y. So if I had a function that was convex and differentiable, then I would know that its gradient granted me this property at a point x. It gave me a tangent line that underestimated the function. Right? It's just this picture we've drawn several times. The right-hand side here is the equation for the tangent line through the point x, and the left-hand side is just the function itself. And a subgradient is kind of a generalization of this notion, in the sense that if you give me any convex function at a point x, then a subgradient g is just a vector that makes such a picture true. Okay, it takes the role of the gradient. And some fundamental properties, we said it always exists for convex functions. And if the function was differentiable at a point, then there's only one subgradient that makes this true, and that's the gradient. Okay, one caveat, I guess I didn't mention it. I only kind of mentioned it in passing last time, but I guess I'll make it explicit, because I did have one question about it after the course, after the lecture. So subgradients always exist for convex functions, and the caveat is that they always exist on the relative interior of the domain. So you know what the interior of a set is. Right? We at least, that's something you should kind of know from some basic real analysis. It's the largest open set contained in your set, or it's the closure of your set minus its boundary. It's two ways to define the interior of a set. So we take the domain, we look at its interior, and this part is technical. I guess I won't even, I could explain what relative interior means, but I don't think it's super important. I just want to emphasize that for some functions that have domains, their subgradients may not actually exist on the boundaries of those domains. So an example was actually just the indicator function. Okay, so the indicator function of a convex set, it's convex, its domain is the set itself. Its interior of the domain is like the interior of the convex set. We don't really think of subgradients as existing on the boundary of the set. Okay, some kind of weird stuff can happen. So just to make it more precise, subgradients always exist kind of in the inside of the domain. Okay, that was just a technical caveat. So we did lots of examples. We talked about some connections to other things we'd seen in the course. And this is where we ended up last time. That subgradients provide you with a way, in a sense, to check optimality. So if I told you that I had a minimized a given function f, then that's true. X star is a minimizer if and only if 0 is a subgradient of my function at the point x star. And that was true without even needing to invoke convexity for the function f, just by definition of a subgradient. Okay, so it's like a one-line proof. If 0 is a subgradient, then we have to have this inequality holding for all y at the point x. Right? And that's just saying that f of y is larger than or equal to f of x star for all points y. So it's equivalent, in a sense, to having found a point x star that minimized your function. Okay, it reduces to the usual rule that you know about when f is differentiable and convex. That's just saying that the the function is minimized if and only if its gradient is 0 at the point x star, right? Because the only subgradients are the gradients of your function. Is that a hand up for a question? No? Okay. So here's an interesting kind of implication of that. We can actually derive the first order optimality condition that we saw like on the second lecture or something, or third lecture, for convex problems where the criterion was smooth and we had a constraint set C. Remember we said that there was this first order optimality condition which says that you have a solution to this problem when f is smooth and convex and C is a convex set, if and only if this was true at the point x. X is a solution if and only if this is true for all other points y. And the way that I kind of explained that was I said that if you were at the point x and you were thinking about moving to the point y, then you form the vector y minus x, right, which points from x to y, and you ask, is the gradient aligned with that of your criterion function? If the gradient is aligned with that, then it means that moving in that direction would only increase the criterion, right? That's the way to think about the gradient. And if that's true for all other points that are feasible, then you must be at the minimum. Okay, so if the gradient is aligned with all other feasible directions, then you must be at the minimum. That's kind of the intuitive way to think about the first order optimality condition. So we can actually prove that from the perspective of subgradients, from what we know so far. Okay, so the first thing we're going to do is just going to recast our problem, this guy, in terms of a problem without constraints, where we've just brought this constraint up to be an indicator. This is just going to be 0 when x is in the set and infinity otherwise in the set C. So these things are equivalent, as we've seen, and we should be comfortable with by now. And now we're going to apply subgradient optimality to this function. Okay, if I have a point that minimizes this function, it's equivalent to 0 being a subgradient of this function at the point. That was what we saw from the last slide. So we want to take subgradients of this function and check when a subgradient is 0. Okay, so how do we take a subgradient of this function, f of x plus the indicator function of the set C at the point x? Well, this guy's convex by assumption, and it's smooth even up here. And this guy is convex because C is convex, right? So we know that for some of our rules for subgradients, we can just take subgradients of f and add them to subgradients of the indicator function. That was one of our first rules. If we had two convex functions, we asked for the subgradients of their sum. I just take subgradients of the first one plus subgradients of the second one. And because we assumed that f was smooth, right, the set of its subgradients at the point x is just the gradient. It's just a set containing the gradient of f at x, right, because f was smooth and convex. And remember, we did this last time. The subgradients of the indicator function of a set C at the point x is exactly the normal cone of the set C at the point x, right? That was this proof that we did here. Okay, it's just a couple of lines. That was something we did last time. Okay, so those are subgradients of our criterion. It's just anything in the normal cone plus essentially the gradient of f at the point x. And if 0 is in this set, right, which contains the gradient of f at x plus anything in the normal cone, that's equivalent to saying that the negative gradient must be an element of the normal cone. Okay, it's just a very simple rearrangement that gives us this, right? If I have something here that's equal to 0, then I must have the negative gradient being an element of the normal cone. But let's just recall what the normal cone meant. The normal cone, right, it was the set of all vectors such that the inner product of that vector with x is bigger than or equal to the inner product of that vector with y for all other points y that are in the set. I guess there's not a y here. Let's just say for all y in the set. Okay, this is just invoking the definition of the normal cone. But rearranging this gives us exactly the first order optimality condition, right? It's just saying that the gradient must be aligned with y minus x. It's just exactly the first order optimality condition. So there you go. We've just proved something that I think is, it's something that maybe one of the first things we learned in convex optimization. And it's also, I think, quite intuitive. And you can see it just follows very simply from checking subgradient optimality and using some properties that we proved last time, like this normal cone being the subgradients of the indicator function. Okay, so that's a demonstration of subgradient optimality. in general, maybe just to take a step back and point out, this condition that we wrote, that we kind of started off with, right? The condition that 0 is, in the set of subgradients of our function plus the normal cone to our constraint at the point x. That is somehow a fully general, necessary and sufficient condition for optimality in a convex problem. Right? That's kind of as general as you can get, because remember, we said we can express all convex problems of this form, or all convex problems of that form. It's just the complications that we usually see in convex problems now are folded into the constraint set. Right? That would kind of encapsulate all of the constraints that we usually write out explicitly. And we, as we just saw, the necessary and sufficient condition for optimality here is that 0 is in the subgradients of the criterion, and these are the subgradients of the criterion. F, I'm just writing it when f is not smooth. So, in a sense, like this is really describing optimality for convex problems entirely. Now, it's not very easy to work with this because this is not usually a very easy thing to work with. If you have a C which is a complicated set, which is defined by, the set of all x for which I have stuff like this holding, it kind of encapsulates my constraints, then constructing the normal cone to the set C at the point x can be quite complicated. It can be intractable. So this is not really necessarily a very useful condition for every convex problem, but it is a necessary and sufficient condition. That later is an equivalent way of posing optimality in convex problems that's just more tractable when you have constraints. Okay, it's equivalent, but it's just easier to work with when you have constraints, and that's going to be called the KKT conditions, the Karush-Tucker conditions. So that'll be usually what we work with when we have convex problems with constraints. Rather than just putting everything into the criterion of indicators and taking subgradients, it's easier to actually use kind of another formulation for optimality. Okay, so just some examples of subgradient optimality beyond that one we just saw. Let's look at subgradient optimality for the lasso. This is, I think kind of interesting. So remember that the lasso problem, we can parameterize it in two ways. One is subject to an L1 norm constraint on the coefficients, so the other is to put this in the criterion. And in either case, we just have a different kind of parameter to think about tuning. That parameter is called lambda here. And okay, let's look at what the subgradient optimality condition would say for this problem, right, where we're doing of y on some predictors x, but we're adding an L1 norm penalty on the weights, or on the coefficients beta. So subgradient optimality would say we have a lasso solution, right, something that minimizes this, if and only if at that point beta, 0 is in the set of subgradients of my criterion, which because these are both convex functions, I can split up this, right, into the subgradients of this plus the subgradients of that. And because this is smooth in convex, the set of its subgradients are actually just its gradient, right? And the gradient of this at the point, at the vector beta, is nothing else than, by the chain rule, x transpose x beta minus y, or I wrote it like this, minus x transpose y minus x beta, because I'm going to want to bring that over to the other side in just a second, right? Plus all the subgradients that I get from the L1 norm. Okay, and again, I'm using another rule here for subgradients. I have a constant times the L1 norm. This is bigger than or equal to 0. It's a convex function, so its subgradients I get just by taking the constant times the subgradients of the L1 norm. Okay, maybe just to be precise, I should have put a set around this gradient here, right? 0 is in the sum of two sets. The set containing the negative gradient, or the gradient rather, plus lambda times the subdifferential. And rearrange that just tells me that x transpose y minus x beta must be equal to lambda times a subgradient of the L1 norm at beta, right? That's all that subgradient optimality is telling me. And let's just recall what subgradients of the L1 norm. We kind of already did this last time, but just to remind you, I can think about a component. This is the vector p. This is the L1 norm acting on a p-dimensional vector. And every component, say if I look at the ith component, that's going to be equal to the sine of beta I if beta I is non-zero, right? So it's 1 when it's positive, and it's minus 1 when it's negative. And if beta I is 0, it's just anything in between minus 1 and 1. Those are the subgradients. So that's the condition for optimality in the lasso problem. If I can find a vector beta that satisfies this for some vector v that is a valid subgradient, which means that it satisfies this, then I actually have the solution. Okay? We're not giving you a way at this point to actually construct the solution. This is just the optimality conditions that characterize the solution. So rearranged, we can actually think about this component-wise. So I'm going to pull out each component of this, okay? And I'm going to compare it to each component of v, because this is an equation that must hold in p variables, right? One for each component, essentially, of the left and right-hand sides. So if I look at the ith component, it tells me that the ith component of that negative gradient, which is nothing else than xi transpose the residual, y minus x beta, must be equal to, well, when beta I is not equal to 0, lambda times the sine of beta I. That just comes from looking at essentially the components of this equation for which beta I are not 0 and invoking the fact that the subgradients over those components are just the sines. Okay, that's this part. The only other thing I have to worry about is the times in which beta I is equal to 0. But in that case, actually, this tells me that the negative gradient can be equal to anything between minus lambda and lambda, right? Because for those, v can be anything between minus 1 and 1. So I can write that kind of more succinctly just by saying that the absolute value of the gradient has to be less than or equal to lambda in those components. Beta I is 0. So this is just another way of writing the last optimality conditions. It's maybe kind of a little bit more succinct. Okay, so this provides us with a way to check optimality, right? If somebody handed you a vector and said, is this optimal with respect to the lasso criterion, you just need to check whether this is true for every component of the vector. Okay, and if it's true, then they have a solution. If it's not, then you tell them that they don't have the solution yet. It's a way to check optimality. It's also, I think, kind of an interesting way to understand the lasso estimator. And a lot of statistical analysis that's been done, and arguably almost all of it, for stuff like the lasso and other convex problems stems from representations like this. Okay, in terms of trying to derive properties of estimators which are defined by solutions of convex problems. Here's one very simple property that you can get out of looking at these conditions. Let's suppose that you solved the lasso with the matrix X. Okay, and let's suppose that X had columns x1 through 100. And you got out a vector beta. Okay, then you know that it must satisfy these conditions, the subgradient optimality conditions. Let's suppose now that somebody came along and they gave you vector more columns of X. So let's say x101 through x200. And they said, actually, I'd like you to solve the lasso on all of these variables. Not just the first 100, but actually on all 200. And you're sitting here with your solution that was the solution for the first 100 variables. So the first thing you can do is you can just check whether this condition is true. Okay, whether this is true for all, check whether xj transpose y minus x beta is actually less than or equal to lambda for all j going from 101 through 200. If that's true, then you don't have to actually resolve the lasso problem, right? You already have the solution, because you can just take the weights that you had essentially already found over these variables and just set them equal to 0 over these variables. Okay? If you do that, then if this were true, you would have satisfied the subgradient optimality condition, so you would have a solution. The question up there.
The x in the last line you wrote, is that the x for columns 1 to 100, or is that the x for columns 1 to 200?
This guy?
Yeah.
Vague in the sense that it doesn't really matter, I don't think, but we can think about this like as, let's just be kind of precise. 1 through 100 times beta 1 through 100. So this is the x that you got originally and the solution you got originally, and that's the fitted value. But I'm proposing that you you actually just think about setting the weights to be 0 here and check the KKT conditions to see whether that's a valid solution. Or I keep saying KKT conditions, so maybe I said that more than once. I mean, I'll mix up the terms subgradient optimality and KKT conditions a few times because they actually are the same when you don't have constraints. So I'm sorry if I'm confusing anybody, but in any case, you just check these optimality conditions. And if I'm setting the weights to be 0 here, then this is the same as like the full x times the full beta. Okay, so that's one thing you can just read off. I mean, it doesn't have to be 100 more variables. Suppose somebody just gave you one more variable and said, solve the lasso again for me. Well, you don't have to call your solver again. You can just check whether or not this condition is true for that extra variable. Okay, and if it's true, then you don't have to solve the problem. You already have the solution. That's one, say, kind of interesting property that you could read off of from these conditions. Another property that you can read off of from these conditions, which is very related to what I just said, is that if somebody hands you, let's say, the fitted values, and they don't hand you the solution, they tell you that actually, I'm going to give you x beta, where beta was optimal. I'll just give you the product of x times beta. That's an n vector. You can look at the inner products of all your variables with the residual. If that happens to be less than lambda in one of the components, then you know that the corresponding component of beta must be 0. Right? Because if that was true, then I must be in the second condition. Right? I could not have gotten something less than lambda if beta I was non-zero. It would have been equal to plus lambda or minus lambda. Okay, so this statement implies that a variable is going to be set to be 0. A coefficient will be set to be 0 at the lasso solution. Okay. Yeah, another question. Sorry, where are we adding sets?
Like 0 is in on your notes.
My notes.
When we're defining the addition for
This?
like how do we define it if both of them have more than one?
Just all the elements of one plus all the elements of the other. So set sum, the set sum between two sets A and B, is just the set of all A plus B, such that A is in A and B is in B. If the set sum is confusing you, then just think about it like I have to find a subgradient of f plus an element of the normal cone that add up to 0. It's another way of thinking about it. Okay, and when one of them just has one element, then it's maybe more easy to think about. But yeah, you had a question.
Isn't normal cone mostly a null set if the point is inside your set?
It's the set containing 0 if the point is inside the set. Yeah.
So, and mostly the minima will not lie at the boundary of the set. Or that would be strange.
No. This is a constraint set, right? So actually, most often it does. It depends on what your constraints are. If the solution lies in the interior of your constraint set, then the constraint's not really active, right? In terms of the problem. So then it's the same as just minimizing the criterion. It's the constraints that kind of will change the nature of the solution. It's a good question, though. Okay. That may become also more clear when we talk about the KKT conditions. I think when it comes to constraints, the KKT conditions are the kind of the easiest and the most standard way to think about optimality. So another example is a much simpler kind of version of the lasso where this X matrix is just the identity. And we're doing something that some people call denoising. We're just solving for the vector beta that is closest to y after I add some kind of L1 penalty. Okay, so you give me a bunch of observations y. I want to find a vector beta that approximates y, but that's sparse. Okay, and this is one way to do that is to solve the lasso problem in a sense when this matrix, I usually think of the matrix of predictor variables as just the identity. I get just one kind of parameter per observation. And with this one, it turns out we can actually solve this directly using subgradient optimality. So when we write down the subgradient optimality conditions, we can derive an explicit solution. It's a very special case. And it's a very useful one too. We'll see this pop up a number of times, I think, from now on when we talk about maximal methods and other things like that. So let's just state what the solution is first. The solution is something called soft thresholding. So I look at every component of y, and I determine the corresponding component of the solution, beta I, via the following expression. So if the ith component of y is bigger than lambda, then I take the ith component of beta I to just be yi minus lambda. Okay, so I subtract a bit off of it. I move it towards 0. If the ith component of y is smaller than or equal to minus lambda, then I add lambda to the ith component of yi to get the solution. Again, I move it towards 0 by an amount lambda. And if the ith component of y lies between minus lambda and lambda, then I set the ith component of beta to 0. This is called soft thresholding. This function, as a function of, its argument, say yi, looks like this, right? Between lambda and minus lambda, you're setting, if I look at this function, plotting this function as a function over just one variable x, then when x is between minus lambda and lambda, it returns for me 0. When x is bigger than lambda, it returns for me x minus lambda. And when x is smaller than lambda, it returns for me minus x plus lambda. Okay, so the solution to this problem, it turns out, is just given by soft thresholding every component of y, one at a time, and then declaring that beta is the result of doing that for each component, on each component. Okay, so let's check that. Let's actually check that that's the solution. We can check it directly from the subgradient optimality conditions. Let's use these ones. Okay, this was like the most, I think, helpful representation that we had for this last one. And here x is the identity for us. Right, so if we do y minus x beta, that's just y minus beta. And if you look at the inner product of the ith column of x with that, that's just the ith component of this. Right, it's the ith component of y minus beta. So these are the subgradient optimality conditions. I just say that, well, yi minus beta I must be equal to lambda times the sign, if beta I is non-zero. And if I'm setting beta I to be 0, then I have to have yi minus beta I being smaller than or equal to lambda. If I can find a beta vector that makes this true, then I have a solution. In fact, I claim I have the solution. Why is it the only solution? It's because this thing is strictly convex, right? Because the first term is strictly convex. So once I satisfy this, I have the solution. So now to check that actually this is the solution, we could have done this two ways. The first is that I could have presented these conditions, and we could have derived soft thresholding from these. Or I could have actually told you what the solution was, and we could have just checked that it satisfied these conditions. Either one would have been fine, but I think it's a little bit easier just to check whether or not this is optimal, soft thresholding. So let's just plug in, right? Plug in for each beta I. Plug in the result of soft thresholding, the corresponding component of yi by the amount lambda. And let's just check that this is satisfied, right, component by component. So if yi is larger than lambda, then we're going to be assigning beta I, right? If yi is bigger than lambda, then we're going to be assigning beta I to be yi minus lambda, which is positive, right, because yi was bigger than lambda, in which case the sign of beta I is 1. And if I look at yi minus beta I, right, by definition, that's just equal to lambda. It's indeed equal to lambda times the sign of beta I, right, because that was 1. And just by definition, right, yi minus beta I is lambda. So I've satisfied the KKT conditions for that. If yi is smaller than minus lambda, then you basically get the same check through some similar arguments. Okay, we're going to see that by the way we've defined beta I, we'll have yi minus beta I being equal to minus lambda. And that'll be actually lambda times the sign of beta I. So it's the same thing. And so now all that's left to check is that when yi is in between minus lambda and lambda, then we still satisfy those KKT conditions, or the subgradient optimality conditions. And in that case, recall by the definition of soft thresholding that we're going to be setting beta I to 0. And okay, yi minus beta I is just equal to yi, right? Because beta I was 0. And that is certainly in between minus lambda and lambda. That's just the assumption in this case, right? So that actually does satisfy the KKT condition still, because all we require, right, is that this residual be less than or equal to lambda in absolute value. Okay, so very simple check showed us that soft thresholding did in fact satisfy these conditions, and therefore it's optimal. Again, we could have gone the other way. We could have written these down and derived soft thresholding. There's kind of no ambiguity there because there's only one solution, right? So it's not like we could have written these down and ended up at a different solution. There's only one solution because the problem is strictly convex. Okay. Any questions about these two examples? So one more example I wanted to do, which is going to be useful in the next set of slides on the subgradient method, is an example for deriving subgradients of the distance function to a closed convex set. So let's suppose that C is a closed and convex set, and we define the distance between any point x in the set C. So think of this as a function of x according to just the minimum over all points y in the set C of the 2 norm between y minus x. So this is a convex function, something we should kind of have in mind and be comfortable with given our stuff on convexity, right? Because this is a convex function of x and y. The 2 norm of y minus x is a convex function in the variable x comma y. And here I'm minimizing. I'm doing partial minimization over some of the variables where the domain for that is a convex set. So that's still convex. So this is a convex function. So we can ask what its subgradients are. Okay, and in fact, there's a pretty interesting thing that comes out of this subgradient calculation, which is that we can show that actually this distance function is differentiable. It's differentiable whenever the point x that you're looking at is outside of the set, whenever it has a positive distance to the set. And if I gave you this this function as a function of x, and I ask you to prove that it's differentiable, that might be kind of a complicated exercise in calculus to do so. But from another perspective, we can actually prove that the set of its subgradients has only one element, right? And when that's true, we know that it's actually differentiable, and whatever that element is its gradient. So it gives us an interesting implication that this function is actually differentiable, provided that we're looking at a point x at which the distance is positive. So I think in the slides, we just show one direction. I just end up showing that this is a valid subgradient of the distance function, but the other direction can be done as well. And I think it may be in some previous notes, or you can come ask me if you're curious. Okay, I just wanted for us to get some practice at working with the subgradient conditions. So we're just going to show that this is a valid subgradient of the distance function. And let me define some of these terms first. We're going to define the projection operator of any point x onto the set C. We're going to denote that by PC of x. And that is defined as, it's just the point that is closest okay, it's the point y that's closest to x among all points y in the set C. So it's the minimizer. And the distance then, right, between x and the point C, it's nothing more than after we've defined this, right, it's nothing more than just the L2 norm between x and its projection onto the set C. So a picture is something like this, right? Here's x. Here's its projection onto the set C. This is the set C. And this is the distance, right? The distance here is just it's the 2 norm between x and the projection onto the set C. The 2 norm of that difference. Okay, so we want to derive subgradients of this function. So we're just going to show this direction. We're just going to show that this guy is a valid subgradient at the point x of the distance function. And let's do so by actually looking at the first order optimality conditions for this problem. Okay, we're going to look at the first order optimality conditions for this problem. Which characterize the projection. Right? The projection of x onto the set C, it actually minimizes this over all points y that are in the set C. And let's look at the first order optimality condition for this problem, right, where y is a variable for a given x in order to kind of characterize the projection. So I think in the notes I called u the projection of x onto the set C. I just called this point u, just so I don't have to keep writing this over and over again. Okay, the first order optimality conditions tells us that the gradient, right, the gradient of my lost function with respect to the optimization variable is y. So the gradient is actually y minus x, right? Let's actually write the problem like this to make our lives easier. So I haven't changed the solutions at all. I'm just changing the criteria by a monotone transformation. The y that minimizes this is still the y that is still the projection. But now I think it's easier to look at gradients of this, right? So I just changed the criterion to that. So the gradients are just, the gradient is just y minus x, the point y. And I'm saying that this transpose let me look at the gradient at the optimal point. Okay, u. The gradient of my loss function at the solution, right, u, transpose y minus x. This must be bigger than or equal to 0 for all y in the set C. This is the first order optimality condition, right? If I take the gradient and take the inner product with the vector that points from x to y, then this must be non-negative for all other feasible points y. That was just this first order optimality condition here, okay? The only confusing bit was that actually, our variable was called u. And again, I'm sorry, I'm making so many typos here. Our variable is called u. That was a record number of like 5 typos on the bottom of the page. Okay, so this is the first order optimality condition. And it helps if we just draw that on our picture. I think it's very interpretable in the case of this projection. So we had u minus x transpose y minus u being bigger than or equal to 0 for all points y in the set C. That's equivalent to x minus u transpose y minus u being less than or equal to 0 for all points y in the set C. So I think we can look at either one. Let's look at this condition maybe. So pick another point in the set. Say pick this point y. So u is the point closest to x in the whole. If I look at the vector that points from let's, I guess, do this one. U to x, that's this vector. And I look at the vector that points from u to y. That's this vector. And they have a negative inner product. Okay, that means that somehow it's saying that the direction from u to y has to be lying below this kind of orthogonal tangent line. Okay, if that wasn't true, right, let's suppose I picked u to be here, and I took, u to x and u to y, then that certainly wouldn't be true, right? The inner product between this vector and this vector would be positive, and u would not be optimal. I'd be able to move it closer to x. Okay, but if I've found a point u that satisfies this for all y, then I have the projection of x onto the set C. Okay, that's all I've drawn right here. And very simple implication of this statement is that the set C is actually contained in the half space, which is the set of all points y, for which this is true. So all I'm saying is that the set of all points y that satisfy this inequality, right, for a given x and u, that defines a half space. That's everything down here. And C is certainly contained in that half space because this inequality is true for all y that are in the set C. Okay, that's just this implication right here. So one thing that I think is very natural to see once you look at this picture, but it's maybe only slightly less natural if you look at it mathematically, is that we can bound the distance between any point y in the set C via this guy right here. Okay, so let me draw it for you on the picture, and then I think we'll do a proof by picture kind of thing. Okay, this is supposed to be true for all y. The distance between any point y in the set C is bigger than or equal to x minus u transpose y minus u over the norm of x minus u. So let's look at a few cases. The first case is, let's look at the case when y is not in the half space H, this half space. Well, in that case, actually, this quantity is negative, right? H was the set of all points for which this was positive. Did I flip the signs here somewhere? Oh, no, I guess I just looked at the wrong condition. If y is in the set H, then the right-hand side is actually negative. Right? By definition, all the points in the half space satisfy this condition. So this is, if we're trying to check this for all y, let's just look at the points y in the half space first. That's clearly going to be true because this is always non-negative distance, and this is actually a negative quantity. If y is not in the half space, then this is where things get kind of a little bit more interesting, but this is where we'll do a proof by picture. Okay, so let's... This is the set H. This is the set C. This is U. This is X. Let's take a point Y here. It's not in this half space below this. It's hyperplane. Then what I'm claiming is that the distance between Y and the set C is larger or equal to this quantity. But this quantity is actually nothing more than the distance between Y and the hyperplane that determines the half space. Okay, so we can get that by looking at, let's first just write actually x minus u transpose y minus u. So that's this vector, right? Inner product with this vector. The norm of x minus u times the cosine of the angle in between, right? It's like a very little basic bit of geometry. The inner product between this and this is nothing more than the length, right, of this part times the cosine of the angle in between them. And that we can actually see is exactly the distance between y and the half space. Right? It's the exact same as this distance. And clearly the distance between y and the half space, which is this guy, is going to be smaller than or equal to the distance between y and the set C because the set C is contained in the half space. Right? If I try to move from y to the set C, it's certainly going to be farther than moving from y to the half space. So then picture, we'll just say then picture works. There's a bit of details, I think, on the slides that just basically maybe only slightly spell it out in more details. Okay, but this is something that we get basically just by looking at the geometry of the optimality condition, is this guy. And now if we plug this into the definition of subgradients, we've essentially now just constructed the existence of a subgradient already with this inequality. Okay, so let's just use this claim and add and subtract x in this second term. Okay, add and subtract x here. So I have that the distance between any point y in my set C is bigger than or equal to this, which we've already established. Add and subtract y. Split up these two terms. The first term you can see, actually it's the second term, is just exactly the distance between x and u. But that's just the distance between x and the set C, right? U is this optimal point. U is the closest point to x in the set C. And what's the second guy? The second guy is just, it actually comes from this inner product divided by this norm. It's just x minus u over the norm of x minus u transpose y minus x. Okay, and this is how we're claiming that this thing is a valid subgradient, because we've proved that for any y, right, we have this expression. Distance function at y is bigger than or equal to distance function at x plus, this is our subgradient g transpose y minus x. That's just the subgradient optimality. So this is just the definition of, subgradients at the point x. Okay, that was the check, yeah.
Maybe I'm missing something, but when the thing that you wrote, x minus u transpose times y minus u, that should be equal to x minus u times y minus u times positive, like the normal. You're just using the that product rule, right? Shouldn't there be another term?
Yes, thank you, yeah, definitely.
It's also on the slide.
Yeah. Thanks. Yeah, it's the product of their, thank you, it's a typo. Product of the norms times the cosine of the angle. Other questions? Okay, so sometimes we have involved calculations like that to verify subgradients or to construct subgradients. This was just, I think, a particularly gradients that we could prove that this function was actually differentiable, or we didn't really prove it's differentiable because we didn't prove both directions, but we at least proved that we had a subgradient. And if you believe me, this is the only subgradient when the distance is positive. And we're going to use this in an optimization problem in the next kind of little bit on the subgradient method. So that, I think, was it. That was it on subgradients. Let me pause before we go on to the subgradient method. Any lingering about subgradients? No? Okay, I think it's probably a good time to take a break then, and we'll come back and do the subgradient method. We're kind of slowly getting more sophisticated. That was the most basic kind of methods, and now we're going to talk about subgradient method, which is still kind of basic, but a little bit maybe more sophisticated in some sense. And we'll continue learning more algorithms, getting more sophisticated as we go along. So last time, to remind you, we looked at a problem in which the criterion was smooth and convex, and we learned this algorithm gradient descent. We just kept moving in the direction of the negative gradient, looked like that. And we proved that it had a convergence rate of 1 over epsilon to get an epsilon suboptimal solution if the gradient was Lipschitz. And in order to kind of get this guarantee, we had to choose the step sizes to be either fixed and small, smaller than or equal to 1 over the Lipschitz constant of grad f, or we had to choose them by backtracking line search. Either one would have worked. And two kind of downsides that we pointed out was that it required f to be differentiable. Gradient descent required that. In this lecture, we'll kind of overcome this. And the other downside is it can be slow to converge. And so next lecture, we'll get at that. Or whenever it is we get to proximal gradient descent and acceleration, it's really acceleration that will fix that. Okay. So what's the subgradient method? So similar setup, but we're not going to assume the function is smooth. So f is going to be convex with a full domain, but not necessarily differentiable. And like gradient descent, we're going to kind of repeatedly move x in the direction of something, but we're going to replace that something, which was originally the negative gradient of our criterion function, by just the negative subgradient, or any negative subgradient of our criterion function. So at each iterate x to the k minus 1, I just look at subgradients of my criterion at the point x k minus 1, and I just pick any of them, call that gk minus 1, and I'm going to update x in the direction of minus gk minus, yeah, gk minus 1. Okay, where this tk plays the role of a step size again. So this is well defined for a convex function, right? Because we always know that there are subgradients, at least if we're staying in the interior of the domain. And one interesting thing, I guess there's a couple interesting things to point out about the subgradient method that make it different from gradient descent. But one thing right off the bat is that we're not necessarily guaranteed to descend on the criterion of the subgradient method. That's why I'm calling it the subgradient method rather than subgradient descent, because it's not necessarily a descent method, even with careful choices of step sizes. So one thing we have to do is we just keep track of the best kind of iterate so far, the one that has the smallest criterion value. And we'll just note that by x, superscript k best, which means that of the iterates we've seen so far, the initializer all the way up to the most recent one, it's the one that has the smallest criterion value. And if we run the subgradient method for, say 100,000 iterations, then instead of reporting the 100,000th iterate, we'll just report the one that we kind of kept track of as being best so far in terms of the criterion value. So what we'll get to in the next 20 minutes is probably just maybe the first two things. And then we'll talk in the next time about a stochastic version of this algorithm and also an interesting intersection of sets problems. So how do we choose step sizes? There are kind of two. Oh, you had a question. Yeah.
So in the algorithm that you suggested, isn't it the case that in one direction, definitely we're going to have a descent?
In one direction.
Seems to me that there are two options, like the negative optical subgradient or the positive values.
But, so it's not always true that if I have, g being a subgradient of my function, that minus g is also a subgradient of my function. That's definitely not the case.
Oh.
So that set doesn't need to be symmetric. So the set of subgradients.
Okay.
Okay. So let's look at these options for step sizes. So the first one is a fixed step size choice, like we do in gradient descent. Just fix it to be something, smallish and the same over all iterations. We'll see that actually what guarantees we get with that are pretty different from what we get with gradient descent. The other option, which is much more common in subgradient method, is to choose step sizes that diminish over iteration. And there are various kind of rules that you can follow in order to choose these diminishing step sizes. One that's pretty common are to choose step sizes that are square summable but not summable. It means that the sums of the squares of the step sizes, if you were to run the algorithm kind of indefinitely, is finite, but the step sizes themselves do not have a finite sum. So we want to make the step sizes go to 0, but we don't want to make them go to 0 too fast. That's what these two conditions are saying. Okay, so what's an example of a step size choice that would meet this? What's an example of a sequence of step sizes tk that I could use? Right, so 1 over k would be a kind of very natural choice. Square, summable but not summable. Example is just take 1 over k. Bonus points for who can tell me what the sum of 1 over k squared converges to. Wow, you guys are good. So there's lots of other options, but the important difference to gradient descent is that we don't have something like adaptive line search. There's no analogy in general of backtracking for the subgradient method, at least not that I'm aware of. Okay, so these are the most common options, something like this or something that's fixed. So the convergence analysis for a subgradient method is in a sense pretty different to what it is for gradient descent. And actually, I think the details are kind of more or less on the slides, just like they were for gradient descent, but I don't want to go through them because it's our uses of complexity, what we've already seen so far, and it's probably better use of our time just to present the results and then move on. But if you have any kind of problems making your way through them, you can come talk to me in office hours. And last year on the second or first homework, I can't remember, maybe the second homework, there was more details on how to prove this. So you can take a look at that too. So here's the result. Let's just state them first. If you have a convex function whose domain is everything, and the function itself is Lipschitz continuous, so before we were assuming that actually grad f was Lipschitz continuous, with subgradient method we're going to assume that the function itself is Lipschitz, okay? Because we're not assuming that the function is actually smooth. So it doesn't make sense to talk about its gradient or anything like that, right? The function itself is Lipschitz with constant, we'll call it g now, right? Which we know just means this. The way the function acts on x and y, the distance between those two is less than or equal to g times the distance between x and y for all x and y. So if that's true, then we can basically present two theorems, one for fixed step size and one for diminishing step sizes, where we define diminishing to mean something that's like, say, satisfies those two conditions, square summable but not summable. So the for fixed step size says that if we were to track the best iterate that we see so far over all iterations, right, running subgradient method indefinitely over all iterations, that the best that we see is less than or equal to the optimal criterion value plus the Lipschitz constant squared, g squared, times t over 2, where t was the fixed step size. So that just means that if you were to run subgradient method forever with a fixed step size 0.1, then you are guaranteed that in the limit you're going to get a 0.05 g squared suboptimal solution. It gives you a guarantee on how far you are from suboptimal. Right? Making t smaller, of course, just makes that suboptimality gap smaller. But it doesn't guarantee that you actually have a solution in the limit. For that, we need diminishing step sizes or other options, but as far as what we've seen so far, just diminishing step sizes. And with those step sizes, you can prove that the best criterion value in the limit is exactly f star. So you get an optimal solution in the limit. Okay, so the different nature of these results are kind of different in nature to those from gradient descent. I'm not going to go through the proof, but basically there's an inequality that we can derive using some very basic arguments involving subgradients and convexity that is of the following form for any step sizes t1 through tk that bounds the criterion value between the best thing we've seen so far after k steps and the optimal criterion value in terms of those step sizes. And from this expression, you can actually just read off directly those two theorems. Okay, you can plug in what happens when each of these ti's is equal to t and take the limit as k goes to infinity to get the first theorem. And you can plug in what happens when when these two conditions, right? This thing having a finite sum, this thing not having a finite sum. I mean, it's summing to infinity. You can also just kind of read off directly that theorem. Okay. R squared, by the way, was the distance between your initial point and an optimal point. Okay, that was R actually. So we had a similar term that we saw in the gradient descent proof. So this is something that I skipped the derivation of, but this is something sometimes people call the basic inequality for a subgradient method, or the basic bound or something. And it gives us both those theorems. And we can also use it to try to investigate something like a convergence rate for subgradient method. So we haven't talked about the rate so far. We just talked about whether or not it converged here, right, at all. Let's talk about the convergence rate. We can also use this basic inequality to get an idea of the convergence rate. And let's pick a fixed step size t. Okay, and if we pick a fixed step size t and we plug it into this bound, then we get the following. After k steps, our best point, its criterion value minus f star, is less than or equal to r squared over 2 times k times t, right, if each of these are just t, plus g squared times t over 2. Right, I have a k times t squared in the numerator, and I have a k times t in the denominator. So all I'm left with is a t in the numerator. So this is our bound on how far we are from optimal after k iterations with a fixed step size t. And if you add equal to epsilon, right, to guarantee that I have an epsilon suboptimal solution, then one thing I could do is try to make each term less than or equal to epsilon over 2. Okay, it's often a good strategy to balance the contributions of two terms that have, they're kind of opposing factors of t and like this. Okay, so I can try to make each term less than or equal to t over 2. So for example, that would tell me to choose t to be based on setting this equal to epsilon over 2. That would tell me to set t to be equal to epsilon over g squared. Okay, and if I plug that in here, I can see that the number of iterations I require, k, ends up being something like r squared g squared over epsilon squared. Okay, so just by setting each of these equal to epsilon over 2, I've determined that I need a step size of about epsilon over the Lipschitz constant squared, and I need a number of steps equal to the square distance between where I start and an optimal solution times the Lipschitz constant squared divided by epsilon squared. So this guy right here is the convergence rate, right? It's how many steps I need to get an epsilon optimal solution. And so we say that the convergence rate is 1 over epsilon squared, right, because of this, treating r and g as constants. So compare that to the order 1 over epsilon rate of gradient descent. We can see it's much, much slower. Right? So think about epsilon being very small. If you want a solution whose accuracy is 0.001 or 10 to the minus 3, then with gradient descent on the order of 10 to the third or 1,000 iterations, right? And as I ask for more digits of accuracy, I multiply this by 10. With the gradient method, actually down the order of 1 over epsilon squared, and as I ask for more digits of accuracy, I have to multiply the number of iterations I take by 100. Okay, so it scales much more poorly in terms of its convergence to high accuracy solutions. So just an example of subgradient method in use versus gradient descent. I tried to think of an example where I could compare them in a way that wasn't totally kind of unfair or crazy, just to give you an idea of how different their convergence behaviors were. So I took this example where I was doing logistic regression, and I had either an L1 penalty or an L2 penalty that I was using. So in this setup, I have predictors xi and I have labels yi, and my yi are just 0 or 1, and I'm trying to do a logistic regression of these labels on my predictor variable. So that's my loss function. It's just the logistic loss. It's the log likelihood under the logistic model. And this is smooth and convex, right? So I can't remember, have we seen this loss before so far in the class? Can you raise your hand if we'd seen it in this class? Oh, I guess I've done this one before. So maybe we'll just spend a second to just certify that this is convex. So this is, as a function of beta, the parameters, that's just a linear term, right? This guy right here. So these are my data, yi and xi, but they're just constants with respect to the optimization problem. This is a linear term, and this is a log sum of exponentials, right? I mean, there's a linear transformation here, but we know that doesn't affect anything, so this is also convex. So I have a linear function plus log sum of exponentials, and then the whole thing is convex. And in fact, it's also twice smooth, and here's its gradient. Or I guess we just need to know that it's differentiable here. Here's its gradient, and it looks like this. It looks very similar to what we know in regression, right? In regression, it's x transpose the residuals. It's very similar here. It's the sum of, again, just the predictors times the residuals, but I replace where I would usually see x beta with my estimate for the mean of y at the point xi in the logistic model, which is just the probability that y is 0, 1. Okay, so it ends up being e to the xi transpose beta over 1 plus e to the xi transpose beta. Okay, so to get this gradient, just you can just think about this, let's say, directly in terms of taking the gradient and using the chain rule. You'd arrive at this expression. Okay, so that's my loss function. That's its gradient, and we're going to consider this problem. So I want to find weight vector beta that minimizes the sum of this logistic loss plus lambda times the penalty, and I'm going to consider two penalties, one that's smooth and one that's non-smooth, so that we can think about using gradient descent and also proximal gradient. So the one that's smooth is going to be the L2 squared penalty, which we often call the ridge penalty. Okay, it's this sum of squares of components of beta. And the one that's non-smooth is the one we've seen several times before, the lasso penalty, just the L1 norm of beta. So right now we only have two algorithms at our disposal, gradient descent and subgradient method, right? There's nothing else in our universe. So if you gave me this, I can run gradient descent. And if you gave me this, I can't run gradient descent because it's not smooth. So I have to run subgradient method. So that's what I'm going to do and show you the difference in convergence behaviors. So I took a problem with 1,000 observations and 20 variables. So I have beta is of length 20, the coefficients I'm solving for. And I'm using gradients for the lasso, and I'm using gradients for ridge and subgradients for the lasso problem, right? Because that's all we can do at this point. And I've hand-tuned the step sizes so that each plot looks favorable for the two methods. Of course, this is a really imperfect comparison, but I'm trying to give you an idea of just the nature of the convergence behaviors for these two methods. So you can see that for gradient descent here, I've plotted f minus f star as a function of iteration. Okay, it converges very, very quickly. Don't look at the scale, just look at the convergence behaviors, say. Because these will be on different scales anyways because of the L1 and the L2 penalties. Well, actually, they probably won't be on very different scales. So actually, the scale is also worth mentioning. Right here, I'm looking at values like 1 to the minus 10. So this is talking about really high accuracy conversions. The subgradient method, I've looked at two different options for the step sizes. So this was a constant step size, 0.001. Here I've used the constant step size 0.001. That's in black. So the first thing to notice is there's nowhere close to descent method, right? It's not even descending anywhere close. It's not even close to descending the criterion. It's bouncing up and down. And it's not clear that if we ran this indefinitely, that actually we'd get anything better than something whose suboptimality gap is around 0.2. It looks like it's pretty much leveled out. Right? So why run it for longer than 200 iterations? That looks like it's the best we can do. If we want to get a more accurate solution, then we have to take a diminishing step size. So here I've taken 0.001 divided by the k. That's my choice of step size at iteration k. That's in red. So you can see it's descending, but it's descending a lot more slowly than something like what gradient descent would be doing. Okay, so it's just a comparison in terms of the convergence behaviors. Maybe one more thing to mention, and then we'll quit. So there's another choice of step size besides diminishing and fixed step size. That's called the. I'm sure I'm saying this wrong. Somebody corrected me this with how to pronounce this at one point who was Hungarian, but I've forgotten. Polyak step sizes. It's probably pronounced not properly. Somebody speak Hungarian? No? Okay, so we'll call them Polyak step sizes. It's probably wrong, the way it's pronounced. If the optimal value is known, then there's a different choice of step size that you can make than diminishing or fixed, and that's this guy. So at the kth iteration, I look at my suboptimality gap between where I was at last iteration, f xk minus 1, and the optimal value itself, f star, and I divide by the norm of the gradient, the subgradient that I picked at the last iteration squared. Okay, and you can actually motivate this as a reasonable choice of step size at the case iteration by looking at the first step in the subgradient proof. We didn't go over this, but the first step in the subgradient proof bounds how far xk is from x star in terms of the last iteration. That choice of step size tk, it actually makes the right-hand side the bound as small as possible. So it gives you the tightest possible bound in that first step of the proof of convergence. That's often how it's presented. If we use these Polyak step sizes, then you can actually prove that the subgradient method converges, which is good. And in fact, it converges at the rate 1 over epsilon squared. So it's the exact same rate that we described before. And that's the rate that we attribute to the subgradient method, okay, in general, whether you use Polyak step sizes or a fixed step size designed to get you a 1 over epsilon, an epsilon suboptimal solution. We'll go over a use of the Polyak step size next time when we talk about the intersection of sets problem. But let me just jump ahead to this last bit like we did with gradient descent, because it's worth pointing out now. So you can ask the same question, which is, can we do better? Okay, we'll talk more about the subgradient method next time. We'll talk more about its applications. But you can ask the same question that we did with gradient descent, which is that we have a rate of 1 over epsilon squared if we're trying to minimize functions that are, let's say, Lipschitz continuous and that are convex. And that seems really slow, right? And certainly in comparison to gradient descent, it's really slow. And you could ask, well, can we do better over that class, right? I mean, is subgradient method just something like not a good choice of method, or is it really at the kind of at the boundary of how well we should be expecting to do? And in order to answer that question, we can formalize something called the class of non-smooth first-order methods. Just like we had first-order methods, non-smooth first-order methods are similar in that they're iterative, and they update at the kth iteration, your iterate, to be something in the span of the subgradients you've seen so far and the initializer. Okay, with first order methods, these were all gradients. But if we think about cases in which the criterion is not differentiable, we're just going to be thinking about taking subgradients. And now there's some trickery, which is, do we get to choose these subgradients, or does somebody have to choose them for us? So here, we're thinking about a situation in which at every step, basically, I arrive at a point xk, and I ask some person, some oracle, please provide me with a subgradient of my loss function at the point xk. And they give us back, say gk. So we don't actually get control over which subgradient you see. And I think that's probably a useful situation to study, because you don't always know kind of the set of all subgradients of certain functions, right? Like we gave at least one example where we only kind of knew one direction, that these things were subgradients, but we didn't actually know what they all were. So this is the model we're looking at, and there's this very useful and I think insightful theorem by Nesterov again. Who else? The same guy who proved the gradient descent lower bound, which basically tells us that we're at the best we can do with the subgradient method. Okay, if you restrict yourself to a non-smooth first order method, then in the worst case, over this problem class of convex Lipschitz functions, you can lower bound the distance you are from from the point x, the suboptimality gap between the point xk and x star by something that is like 1 over the square root of k. And in terms of epsilon notation, this tells us that the 1 over epsilon squared convergence rate is optimal. So once we see this, we have to be thinking a few things. The first is that even though the subgradient is slow, we really shouldn't be expecting to be doing any better unless we're trying to go outside of this class of methods. Okay? Maybe just looking at subgradients and adding subgradients and moving in the direction of subgradients, we can't really do much better than the subgradient method if that's the class of methods we're going to be thinking about. So that's one direction that you'll learn in an optimization course. You'll start talking about methods like cutting plane methods, or interior point methods in some sense are well outside of this class of methods. But that's kind of, I think, one direction you can go. The other direction that you can go is you can say, well, maybe these functions, convex Lipschitz functions, that's just too broad. I should be starting to think about optimizing functions that are non-smooth but have more structure, right? Because this is a very big class of functions, and this is like, you can see over this class of functions, this is somehow the best you can do. And that's the direction we're going to take, at least right now. In a few lectures, we'll start talking about problems in which our criterion has a non-smooth part and a smooth part, but that non-smooth part is actually somewhat simple and structured. Okay, so we're going to be looking at more kind of somehow specialized functions rather than just functions that are convex and Lipschitz. And we'll see we can actually make huge improvements on the convergence rate for these specialized functions. And those specialized functions are pretty relevant in the sense that they still define a bunch of engineering problems. Okay, so that was it. I will see you guys on Monday.